This is Algebra 2 at Bangor Christian Schools. We're going to do lesson 1.5, Properties of Exponents. Let's pray. Father, I thank you for your kindness and your goodness. I thank you for the students you've given me. There's a lot to do today. There's a lot of detail today. Your word have we hidden in our heart that we might not sin against you. And that's a lifelong process that comes by taking in your word, understanding your character, understanding who you are, loving what you love and hating what you hate. Now this lesson has a lot of details, and so my students are going to have to practice quite a bit with this lesson. So I pray for their encouragement, that they would just have the motivation to just stick with it and to continue to practice with this lesson. Help me to be a blessing to them today. We praise your name. We thank you for what Christ has done on the cross for us. We give you all praise in Jesus' name. Amen. All right, let's get right into it. Our objective today is to simplify expressions involving exponents and to use scientific notation. So before we get into the examples, let's just go ahead and look at what we're talking about here. We have a number, a real number a, and raised to some kind of a power. So a to the nth power can be represented as a times itself n times. And so there are n factors of a here. A is called the base. N is oftentimes called the power or the exponent, but I'm also going to use the other name that it's not often called, but you'll need to know it because it's going to come up in the future. So N can be called the exponent, but sometimes it's also called the logarithm, and that becomes important in later lessons. But for this lesson, you can just call it the power or the exponent, and that's fine. All right, let's go ahead and get right into example 1. Writing exponential expressions in expanded form. The base is 5w. The parentheses indicate that this is being repeated 3 different times. The power is 3. And so expanded form, what we do is we rewrite the base within the parentheses, the number of times that the power indicates. And so this is 5w times 5w times 5w. Now I arrange my 5s like so. 5 times 5 times 5 times w times w times w. And that right there is called expanded form. Expanded form. Negative b to the 4th power. Now the negative, what that actually means when I have a negative in front of the base like this means negative 1 times b to the 4th power. And since there are no parentheses, there's no grouping around the negative 1, that means that the negative 1 is not to be repeated. It's just the base of b that's to be repeated. So this becomes negative 1 times b times b times b times b. And that's the expanded form. All right, let's go ahead and look at 3xy cubed, x minus y to the 4th power. X is not being raised to the 3rd power. It's just the base of y. So this becomes 3x y times y times y. And then this binomial of x minus y is being raised to the 4th power. So this is repeated 4 different times. So this is x minus y, x minus y, x minus y, x minus y. And there's the expanded form. And so now this is something you'll be expected to do. Know how to write exponential expressions in this expanded form. So you'll have plenty of different examples for that. We've got 7 properties to deal with in this lesson, and that's a lot. So we're going to have to do a lot of practice. So let me introduce you to the first 2 properties. The first one's called the zero exponent property. And it says this: if a is a real number, and it can't be 0, by the way, so that's the only real number it can't be. But so long as it's a real number that's not 0, then a to the 0 power will always be the number 1. Always. And I will show you later in the lesson why that's the case. But for right now, let's just accept that as the truth. Because it is the truth, but let's accept it as the truth. The second property says this. This is the negative exponent property. It says let a be a real number such that a is not 0. So again, we cannot have 0. If n is greater than 0, then a to the negative n can be written as a reciprocal. A to the negative n can be written as 1 over a to the positive n. And so anytime you have a negative power, you can reciprocate the base and write it as a positive power. Okay, so the 0 exponent property and the negative exponent property, we're going to have to get familiar with those and how to use them. So, okay, now we're here in example 2, simplifying expressions with negative exponents. Here I've got 3 to the negative 4 power, so I'm going to use the negative exponent property. I'm going to write the base as a reciprocal. And so the reciprocal of 3 is 1/3, so this becomes 1 over 3 to the 4th power. And it didn't ask me to go any further, so I'm going to leave it as so. This negative 3 means I'm going to take the base of 2/3 and write it as a reciprocal. But this negative outside the parentheses is just a negative 1. So technically, this is negative 1 times 2/3 to the negative 3. So this does not get reciprocated. The base of 2/3 does get reciprocated. And so this is equal to negative 1 times 3 over 2 to the positive 3, like that. So when I reciprocate the base, I can then swap the negative power for a positive power, and now we're done. So we've used the negative exponent property 2 times now. Let's jump into a warning. There's something we've got to be careful about because it's easy to fall into. It's a misconception it's easy to fall into. And it's this. Let's not confuse a to the negative n with negative a to the n. So in other words, a negative power does not mean that the base is negative. That's not what we're communicating here. A negative power does not mean that the base is negative. All a negative power means is that we're going to reciprocate the base. It has nothing to do with whether the base is positive or negative. Okay? All right, so we've talked about our first 2 properties. Now we're going to get into, there we go. We're going to get into our next 5 properties. So again, we have a total of 7 properties in this lesson. We've got to talk about the properties of exponents, all 5 of these. So let's go through them one at a time. Here's the first one. It's called the product of powers property. Here's what it says. If a is a real number, then a to the power n times a to the power m is the same value as a to the powers of n plus m. So if I have the same base, excuse me, if I have the same base and I'm multiplying the same base, I'm allowed to add their powers. So a to the n plus n. Here's an example. 4 to the 2nd power times 4 to the 3rd power. I have the same base of 4. So this becomes 4 to the 2 plus 3, which is 4 to the 5th power. That is the product of powers property. Okay? Let's get to the next one. The quotient of powers property. If a is a real number and a is not equal to 0, then a to the n power divided by a to the m power is the same thing as a to the n minus m. And so I can subtract the powers so long as I have the same base of a. Here's 5 to the 5th power divided by 5 to the 2nd power. So this becomes 5 to the 5 minus 2, which is 5 to the 3rd. And that's the quotient of power property. Now I can actually go back and show you why the 0 exponent property is true. Let's say I have 5 to the 5th divided by 5 to the 5th. And I'm going to need to move my camera back. That's perfectly fine. Let's move the camera back. Right here, 5 to the 5th divided by 5 to the 5th. Well, it's the same exact power, same exact base. We know that's the number 1, right? But if I use my quotient property that I just illustrated to you, I could say 5 minus 5. So this is 5 to the 5 minus 5, which is 5 to the 0 power. And so that's why everything to the 0 power, if it's a real number, and if that real number is not 0 itself, 5 to the 0 is 1. And so that's the reason why. All right. Let's get into the, oh, I need to move the camera just a little bit here. Let's see. Nope, wrong way. Okay, there we go. Let's look at the power of a power property. Power of a power property. If base A is a real number, then A to the n raised again to the m is the same thing as A to the nm, n times m. So if I have a power to a power, I can multiply the powers. So here's 3 squared raised again to the 4th power. So 2 times 4 is 8. So it becomes 3 to the 8th power. All right, let's go ahead and look at the power of a quotient property. Too far. There we go. Power of a quotient property. If A and B are real numbers, and B is not 0, because you can't divide by 0, that's undefined, then the ratio of A to B raised to the n power is exactly the same as A to the n over B to the n. So in other words, the power comes in like so, A to the n over B to the n. Here's 3/4 raised to the 3rd power. And so this property says that this can be rewritten as 3 cubed over 4 cubed. And that is the power of a quotient property. Okay, 1, 2, 3, 4, 5. We just talked about the last 5, making a total of 7 properties. Make sure these get into your notes. You're going to have them, and you're going to have to learn them and memorize them and know how to use them. Okay? So let's look at another example. Using properties of exponents to simplify expressions. So, what do I have here? I have 2x cubed y times 5x 6y plus 2. I'm about to use the distributive property. So, I multiply the coefficients 2 and 5, that gives me 10. But x cubed times x, I add the powers. 3 plus 1 is 4. So this is 10x to the 4th times y, and that's the first term. Now I multiply the coefficients, 2 and 6. 2 times 6 is 12. I carry the x cubed in, and then I add the powers for y. 1 plus 1 is 2, so this is y squared. Now I take the coefficients, 2 times 2, that's 4. And since this has no xy part of the term, I just rewrite x cubed y. And now it's completely distributed. I'm done. This is actually a negative dm cubed over d squared, all to the 4th power. And notice the negative sign is on the outside. That's important because that means that this is a negative 1 times the whole thing. So the final answer should still be negative. Now what I'm going to do first is I'm going to use my, let's look at it real quick, my quotient of powers property. This is d to the 1st. This is d to the 2nd. So 1 minus 2 is negative 1. So this becomes negative, parenthesis, d to the negative 1, m to the 3rd, all raised to the 4th. So I subtracted the powers of d. Now I use my power to a power property. Negative 1 times 4 is negative 4. So this becomes d to the negative 4. 3 times 4 is the number 12. So this is m to the 12th power. Now I'm going to use my reciprocal property. This base of d is being raised to a negative power. So the reciprocal is 1 over d to the 4th power. So this becomes 1 over d to the 4th power times m to the 12th. And now I can merge the two together through multiplication. This becomes negative, by the way, that's still negative because of the negative sign, m to the 12th over d to the 4th, and it's negative. And so there's the final answer. Let's review it again real quick. Started with a negative on the outside because it's -1. This whole thing is being raised to the 4th power. First thing I did was I took the powers of d, 1 minus 2. That gave me d to the -1. Then I used my power to a power property. So -1 times 4 is -4. 3 times 4 is 12. So now I have negative d to the -4 m to the 12th. Then I noticed that this has to become a reciprocal. So this becomes 1 over d to the +4. So now there's the negative sign outside. -1 over d to the 4th. Notice it's a +4 times m to the 12th. And then I can merge those back together. So negative m to the 12th over d to the 4th. Okay? All right. In this lesson, we also want to know how to deal with scientific notation. So it's perfectly fine that we're going to you have to use a calculator to do this. This is how we're going to do this kind of a problem. First thing we're going to do is we take the powers of 10 and we subtract. So -3 minus 8. So this becomes 9.1 divided by 1.3 times 10 to the -3 minus 8. Calculator time, 9.1 divided by 1.3 is the number 7. That was actually pretty good. Times 10 to the -11. And so 7.0 times 10 to the -11 is the final answer here. Now I have 3.5 times 10 to the 8th times 5.2 times 10 to the 5th. When you multiply the same base, you add the powers. And so this is 3.5 times 5.2 times 10 to the 8th times 10 to the 5th. So we're going to we're going to add the powers of 8 and 5 and get 13. Now let's take 3.5 times 5.2. We get 18.2 times 10 to the 13th power. Now, we can't leave it that way because that's not scientific notation. Scientific notation says that the number being multiplied by 10 to the power, that number can be 1 digit and then the decimal. So it has to be 1 digit and the decimal. So what I have to do is I have to convert this 18.2 into a 1.82 times 10 to the 1st power, and then multiply by 10 to the 13th power. So I have to move the decimal one space to the left, and that's why 18.2 becomes 1.82 times 10 to the 1st. Now I use my property. Like the base is multiplied means we add the powers. Final answer, 1.82 times 10 to the 14th power. And now we've simplified it completely. So here's example problem 5. It's a stellar application. So let's read through the problem first, make sure we understand the problem, and let's make sure we understand what's being asked of us. We think that light travels through space at 3.0 times 10 to the 5th kilometers per second. There's a lot of evidence for that. How many minutes does it take light to travel from our sun to Saturn? Let's underline what's being asked of us. How many minutes does it take light to travel from our sun to Saturn? So what we're hunting for is minutes. The speed of light is 3 times 10 to the 5th kilometers per second. And this table illustrates distances from the sun to the planet. Here's Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. For those of you out there, I did leave out Pluto, although Pluto's near and dear to my heart. For example, Earth, this would represent 1.5 times 10 to the 11 meters distance from the sun. Now we want to figure out the time it takes in minutes for light to travel from the sun to Saturn, so we're going to use this distance right here. 1.4 times 10 to the 12 meters. Okay, let's see if we can figure some of this out right here by doing some math. We know that distance is equal to speed times time. Distance equals rate times time. That's just the natural formula that comes. So the time that we're hunting for is the distance divided by the speed. That's how we find time. Now, I do have to do a conversion because my speed is in kilometers per second. I don't want that. I want meters per minute. So how do I get around that? Well, 1,000 meters is 1 kilometer. So I can replace a kilometer, the km unit, with 1,000 meters. That's totally justifiable. And 1,000 is the same as 10 to the third power. Now, if I do this conversion here, it takes 60 seconds for 1 minute. So I multiply by 60 seconds over 1 minute. That's a fancy form of 1. The seconds divide out. So I'm left with 3.0 times 10 to the 5th times 10 to the 3rd, that's my 1,000, times 60, which is 6 times 10, meters over minutes. I break this up into 6 times 10, and 6 times 3 is 18. 10 to the 5th times 10 to the 3rd times 10 to the 1st is 10 to the 9th. So now I've got 18 times 10 to the 9th meters per minute. Those are the units that I want. So now I'm going to use my time equals distance divided by speed formula. So I've got 1.4 times 10 to the 12th meters divided by 18 times 10 to the 9th meters per minute. 1.4 divided by 18, well, that's 0.07 repeating, times 10 to the 3rd. 12 minus 9 is the power 3. Minutes. The meters cancel out, the minutes reciprocate, so I have minutes now as my units. Move the decimal over 3 spaces. That gives me 77.7 repeating, or 77.8 minutes. So that's how long it takes light to reach from the sun to Saturn. Just over an hour, just about just about 77 minutes. So yeah, about an hour and 18 minutes is how long it takes light from the sun to reach Saturn. Think about that. That means that if you're on Saturn, which doesn't have a surface, but if you're really close to Saturn, when you look at the sun, you're actually looking an hour and 17 or an hour and 18 minutes in the past. You're not looking at what's happening to the sun right then. You're actually looking in the past by an hour and 18 minutes. That's cool. I think that's cool. All right, and that is our distance application. Let's leave with the verse today. 1 Peter chapter 5, verses 6 through 7. Humble yourselves under the mighty hand of God, that he may exalt you at the proper time, casting all your anxieties upon him, because he cares for you. Where should we be? Or what should we do? That's the first question. According to that verse, we should humble ourselves. Second question, where? Answer, under the mighty hand of God. For what purpose? So that he might exalt you at the proper time. What should you do after you've humbled yourself under the mighty hand of God, casting all your anxieties upon him? Why should you do this? Answer, because he cares for you. God bless you, wherever you are today.
That's no moon. It's a space station.
It's too big to be a space station.